Okay? So, right now, without moving, you are near the center of the largest known emptiness in the observable universe. It is called the KBC Void. It is approximately 2 billion light-years across. It contains you, me, the Milky Way, the local group, most of the Laniakea supercluster, and every single telescope human beings have ever pointed at the sky. We have been measuring the universe from inside this hole for our entire scientific history, and we only confirmed it was a hole in 2013. Which raises a pretty reasonable follow-up question. If every cosmic map was drawn from inside an enormous underdensity, what does the universe actually look like from outside it? Subscribe if you're new, get cozy. This one goes deep, and we are not leaving until we find out. Part 1. You are already inside it. Right now, without moving an inch, without looking up, without doing anything at all, you're inside one of the largest known structures in the observable universe. Not near it, not adjacent to it, inside it. You're sitting, right now, near the center of an emptiness so enormous that if you tried to cross it at the speed of light, the fastest anything in the universe is allowed to travel, the journey would take approximately 2 billion years. 2 billion years of travelling at 299 million meters per second, every second without stopping, and you still would not have made it out the other side. That is where you live. That is where every human being who has ever existed has lived. That is where every telescope ever pointed at the sky has been sitting when it took its measurements. The structure is called the KBC Void. Some call it the local hole. And the reason most people have never heard of it is not because it is controversial or fringe or disputed. It is peer-reviewed, independently confirmed astrophysics, published in respected journals, studied by serious researchers at serious institutions. The reason most people have never heard of it is simply because the human mind was not built to process what it means. So we hear it, we nod, we move on, and we do not sit with the weight of it long enough to feel it properly. Tonight, we are going to sit with it. Here is what we know. The KBC Void stretches roughly 2 billion light-years across. Inside it, galaxies are between 15 and 50% rarer than they are in the cosmic average, which means if you were standing outside this void, looking in, you would notice a conspicuous dimming, a region of space that just has noticeably less stuff in it than the surrounding universe. And sitting inside that underdense region, near the middle of it, is our galaxy, the Milky Way. Alongside the Milky Way sits the local group, the few dozen galaxies gravitationally bound to us, and surrounding the local group, stretching hundreds of millions of light-years in every direction, is the Laniakea supercluster, the enormous cosmic structure that is itself a kind of local neighborhood, and even most of that sits inside the KBC Void too. Everything we have ever observed, every star catalogued, every galaxy photographed, every measurement of cosmic expansion ever taken, all of it was done from inside this hole, and that matters in ways we are only beginning to understand. The confirmation that we live inside this underdensity is relatively recent. The scientific community had hints of it for years, anomalies in galaxy counts, subtle inconsistencies in how the local universe seemed to behave compared to predictions. But it was not until the early 2000s, and especially a landmark paper published in 2013 by researchers Ryan Keenan, Amy Barger, and Lennox Cowie, that the case was made rigorously enough to get serious attention. They mapped the distribution of galaxies across a large region of the local universe and found, clearly and consistently, that we are sitting inside a significant underdensity. Independent studies using different methods, supernova counts, luminosity surveys, infrared measurements, have since corroborated the finding. This is not one team's anomaly. Multiple lines of evidence, using different instruments and different techniques, all point at the same conclusion. So let us think about what that actually means. When scientists measure the expansion rate of the universe, they are looking outward from here. When they calculate how fast galaxies are receding from us, they are doing it from inside a region where galaxies are already rarer than normal, where the local gravitational landscape is different from the cosmic average. Think about that for a moment the way you would think about a measurement error, except it is not exactly an error. It is a vantage point problem. Imagine trying to measure the average temperature of the entire ocean while floating inside an unusually warm current. Your thermometer is working perfectly. Your readings are accurate for where you are, but where you are is not representative of the whole. That is the situation cosmology has been quietly grappling with. What makes this genuinely unsettling, in the best possible way, the way that good science should occasionally unsettle you, is that this was not a deliberate choice. No one decided to set up their telescopes inside a cosmic void. No one knew it was there when the first redshift surveys were being conducted. The bias crept into every measurement silently, invisibly in the background for decades. And now that we know it is there, we have to go back and ask, how much did it skew things? How much of what we think we know about the universe is actually a description of the universe, and how much of it is a description of our peculiar corner of it? That question does not have a clean answer yet, and that is precisely what makes it worth spending time on. But to really feel the weight of this, to understand why the KBC void is as significant as it is, we need to take a step back. Because the KBC void is not some isolated quirk. It is not a one-off curiosity. It is part of a vast interconnected architecture of emptiness and structure that runs through the entire observable universe. And once you understand what that architecture actually looks like, once you understand that voids are not the exception but the rule, that emptiness is not the absence of the universe but its dominant form, the fact that we live inside one becomes even more extraordinary. To get there, we need to talk about what empty actually means, because if your mental image of deep space is a place with no stars, no planets, nothing at all, then I'm about to introduce you to something far stranger. The universe has gradations of emptiness that go well beyond anything our ordinary intuitions can prepare us for. And the void at the bottom of that ladder, the kind of void we actually live inside, is not just a place with fewer galaxies. It is a different kind of place entirely, and understanding why changes everything about how we interpret the measurements made from inside it. So hold that thought. Because the story of the KBC void starts, as most of the universe's best stories do, with the strange and humbling fact that what we called emptiness was never really empty to begin with, and what we called full was never really typical. Part 2. Empty is not what you think. There is a version of empty that you know, the space between the furniture in your room, the air inside an evacuated jar. Maybe, if you are feeling poetic about it, the gap between stars on a clear night. But every one of those things is, by cosmic standards, impossibly, almost offensively crowded. The universe has levels of emptiness that do not have good analogues in everyday life, and the only way to really understand what we mean when we call something a void is to walk down the ladder rung by rung until we reach the bottom, and then keep going. Start where you are. The air around you contains roughly 2.7 times 10 to the 25th molecules per cubic meter. That is a 25-digit number of molecules in a space you could carry in a bucket. Already, this is beyond what human intuition was built to handle, but reduce the pressure to the best vacuum achievable in a laboratory, a so-called ultra-high vacuum, and you're down to around 10 million molecules per cubic meter. Still an enormous number, but already 100 billion times less dense than the air in the room. Step outside Earth's atmosphere entirely, into low Earth orbit where satellites circle, and you're down to around 10 trillion particles per cubic meter, still more than the laboratory vacuum, because we are not out of the atmosphere yet, just in its outermost, most tenuous fringe. Keep climbing. By the time you are in interplanetary space, the region between Earth and Mars, say, you're looking at around 10 million particles per cubic meter, mostly hydrogen and helium ions in what we call the solar wind. Still not nothing. Not even close to nothing, cosmically speaking. Push out further, out past the planets, past the heliopause where the solar wind ends and interstellar space begins. You're now in the interstellar medium, the thin gas and dust that fills the spaces between stars within a galaxy. The density here varies enormously depending on where you are, ranging from around 1 million particles per cubic meter in denser clouds down to perhaps 100,000 in the more typical regions between them. That is somewhere between 10 and 100 atoms per teaspoon of space, almost nothing, but not quite. Now leave the galaxy. Cross the enormous gulf of space between the Milky Way and Andromeda, roughly 2.5 million light-years, and you're in the intergalactic medium. The gas here, such as it is, has a density of around 10 particles per cubic meter. 10 atoms in a space the size of a cubic meter. A cube 1 meter on each side containing 10 hydrogen atoms, nothing else. If you scooped up that cubic meter of intergalactic space and brought it to a laboratory, the most sensitive instruments available would barely detect that anything was there at all. By the standards of everything we experience on Earth, this is effectively nothing. But here is the thing. That is the average. That is what you get in the general intergalactic medium. The regions between galaxy clusters, between the filaments and walls of the cosmic web, but not yet in the most underdense regions. Step into a void, a genuine cosmological void like the Boötes Void or the cavity regions within the KBC void, and the density drops even further. In the interior of a typical supervoid, the matter density can be as low as 10 to 20% of the cosmic mean, which means that in a region that was already almost incomprehensibly sparse by human standards, you subtract another 80 or 90% of what little is there, and you get what cosmologists call an underdensity. What does that look like in practice? It looks like a region of space with almost no galaxies, where outside a void you might expect to see hundreds of galaxies per survey volume. Inside one you might see dozens, or fewer. The space itself is not truly empty. Dark matter likely still permeates it. Cosmic background radiation fills it uniformly. The occasional lonely galaxy drifts through. But structurally, gravitationally, in terms of the matter and light that built everything we have ever called the universe, voids are as close to nothing as the universe gets. And this is where the central thread of our story reasserts itself in a way that should stop you cold. Because we have just established that there is a meaningful, measurable difference between void space and the cosmic average, void regions are genuinely physically different from the rest of the universe. They expand faster, they interact with light differently. The local gravitational field inside them is not representative of the universal average, and that means that every single cosmological measurement ever made, every distance estimate, every expansion rate calculation, every map of the large-scale structure was made from inside a region that is, by the universe's own standards, anomalous. Our telescopes work perfectly. Our mathematics is sound. But we've been measuring the universe from inside one of its least typical neighbourhoods, and we have only recently started to understand what that means. Before we can go deeper into that, though, we need to understand what kind of universe produces these voids in the first place. Because the emptiness is not random. It is not just gaps left behind by some cosmic bad luck. The voids are part of a structure, a pattern so enormous and so elegant that when it was first properly mapped, it changed the way scientists thought about the universe at the larger scales. That structure has a name, and once you see it, you cannot unsee it. Part 3. The universe is upside down. Here is something that took the scientific community most of the 20th century to fully accept. The universe, at the largest scales, is not spread evenly. It is not a uniform distribution of galaxies scattered like a powder across the sky. It is not even close to that. What it actually is something that most introductory astronomy courses do not spend enough time on. Because once you properly absorb it, it makes the universe feel radically different from the place you thought you were living in. The universe is mostly empty. Not mostly full, with some gaps. Mostly empty, with thin threads of matter draped across the emptiness like a cobweb stretched over a dark room. This structure, the arrangement of matter at the largest scales, is called the cosmic web. And the cosmic web has three main components: filaments, walls, and nodes. Filaments are long, thin strands of matter, hundreds of millions of light-years long, where galaxies cluster along gravitational pathways. Walls are flat, sheet-like structures, broader but thinner than filaments, where galaxies accumulate in roughly planar arrangements. Nodes, sometimes called galaxy clusters or superclusters, are the densest points where filaments and walls intersect, the bright knots in the web where matter has accumulated over billions of years into enormous gravitational piles. And then there are the voids, the spaces between all of that, the regions that are not filaments, not walls, not nodes. And here is the number that recalibrates everything. By volume, voids occupy approximately 60 to 80% of the observable universe. Let that land. The matter, the galaxies, the stars, the gas clouds, the dark matter halos, all of it, the entirety of what we typically call the universe, is compressed into roughly 20 to 40% of the available volume. The majority of the universe's space, more than half of everything, is void. The dominant form of the universe is not matter, it is absence. Think about that in terms of your intuitions about the cosmos. When you look at photographs from the Hubble Space Telescope, those iconic images of galaxy fields where thousands of galaxies dot the frame like lights on a city at night, what you're seeing is a slice through the nodes and filaments, the dense regions deliberately targeted because they are where the interesting objects are. The photographers are not pointing the telescope into a void. Nobody makes poster-worthy images of a region of space that contains almost nothing. So our visual intuition about the universe is systematically biased toward the crowded parts, the exceptional minority of space where matter accumulated, and we have systematically underrepresented the vast, quiet, dominant majority that is emptiness. This discovery did not happen overnight. The first evidence that the universe had large-scale structure came from galaxy surveys in the 1970s and 1980s, when astronomers began mapping the three-dimensional positions of galaxies in sufficient numbers to see patterns. The Sloan Digital Sky Survey, or SDSS, eventually mapped the positions of more than 300 million astronomical objects across roughly a third of the sky, and the resulting maps showed the cosmic web in extraordinary detail. Long, glowing filaments of galaxies arching across the sky, connected at dense cluster nodes, with wide, dark regions between them. The foam of a soap bubble, or the structure of a sponge, are the most commonly used analogies, and both capture something true. The matter is a thin skin on the surface of much larger, mostly empty cells. And the reason this matters for our central story, the reason it is not just a background fact but a direct part of understanding where we live, is that the KBC void is not an isolated anomaly sitting by itself in an otherwise uniform universe. It is a component of the cosmic web, one of those large void cells, but one that happens to be enormous, one that happens to be nearby, and one that happens to contain us. We are not just living in the universe, we are living in one of its voids, one of the dominant majority structures. And understanding the cosmic web makes it clear that our position is not merely unlucky or random. We are sitting where most of the universe's volume sits, in an underdensity surrounded by walls and filaments of matter that mark the boundaries of the structure we are inside. The question that the cosmic web raises, and which the next 100 million years of cosmology will be trying to answer, is whether our position inside this void has been quietly distorting our picture of reality all along. And to understand that, we first need to go somewhere smaller, a void with a name, a void with a story, a void that was, for many astronomers, the first true confrontation with what cosmic emptiness actually looks like up close. Part 4. The first hint. Something was wrong. Before anyone knew about the KBC void, before anyone had mapped the cosmic web in enough detail to see that emptiness was the norm rather than the exception, there was a growing unease in the astronomical community. It started quietly, as these things usually do, in the margins of surveys that were designed to do something else entirely. In the 1960s and 1970s, astronomers began the slow, painstaking work of conducting redshift surveys, measuring the spectra of large numbers of galaxies to determine how fast they were moving away from us, and from that, how far away they were. The goal was to map the three-dimensional distribution of galaxies in the local universe, and the assumption going in, the assumption baked into the foundational equations of cosmology since Einstein and Friedman and Hubble, was that on large enough scales the universe would look more or less the same everywhere. Smooth, uniform, isotropic. This is called the cosmological principle, and it was not just a guess. It was a necessary assumption for the mathematics of general relativity applied to the universe as a whole to produce sensible results. The survey started revealing something inconvenient, not gradually or subtly, but with an almost rude abruptness. The galaxies were not distributed uniformly. They were clustered in some regions and almost entirely absent in others. The first major surprise came in the survey work of the mid-1970s, when patterns started emerging that were too large, too coherent, and too consistent to be explained away as statistical noise or instrument error. Astronomers began seeing walls of galaxies, dense sheets hundreds of millions of light-years long, and between them, regions that were conspicuously uncomfortably empty. The skepticism was entirely predictable. In science, when your data contradicts your foundational assumptions, the first response is almost always to question the data. There were debates about whether the apparent voids were real structures or observational artifacts, gaps in the survey coverage, or biases introduced by which galaxies were bright enough to detect. But as the surveys improved, as more telescopes pointed at more parts of the sky and measured more redshifts, the structures only became more clear, not less. The universe was not smooth. It was lumpy, at scales that the cosmological principle should have prevented. The 1980s brought the first properly systematic maps. Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics produced what became known as the slice of the universe maps. Elegant cross-sections showing galaxies as dots in a thin wedge of sky, and revealing, for the first time in a single compelling image, the filamentary, web-like structure of the local universe. The maps showed the Great Wall, a sheet of galaxies roughly 500 million light-years long, and between it and other structures, the clearly visible voids. When those maps were published, they were genuinely surprising. Not just to the public, but to working cosmologists who had spent careers assuming the universe at large scales was more or less smooth. What was becoming clear, though no one quite stated it this directly at the time, was that the universe had a preference for structure, and that structure had two complementary aspects: the matter that concentrated into filaments and walls, and the emptiness that those filaments and walls left behind. The voids were not failures of the universe to fill a region with galaxies. They were the inevitable result of the same gravitational dynamics that created the galaxies in the first place. Matter flows outward from underdense regions and inward toward overdense ones, and as it does, the underdense regions grow more underdense and the overdense regions grow more overdense. The web forms, and the voids, are as much a product of cosmic structure formation as the galaxy clusters are. This realization, that voids are not gaps but features, set the stage for the real shock. Because if voids are features, if they are large, coherent, gravitationally meaningful structures in their own right, then the discovery that we live inside one is not just a coincidence. It is a feature of our particular position in the cosmic web. It is a fact about our cosmic address, and addresses, as we all know, affect your perspective on the neighborhood. The question is, by how much? Part 5. The Great Nothing. In 1981, a team of astronomers led by Robert Kirshner published a paper that stopped the astronomical community in its tracks. They had been conducting a survey of galaxy redshifts in a region of the sky toward the constellation Boötes, and what they found there, or rather what they found not there, was so unusual that it required a new vocabulary. They called it a void. We now call it the Boötes Void, and for decades after its discovery it held the title of the largest known structure of its kind. The Boötes Void is roughly 250 to 330 million light-years across, depending on exactly where you draw its boundaries. To put that in the kind of context that actually lands, if you took our entire Milky Way galaxy, a structure that contains somewhere between 100 billion and 400 billion stars, a structure so enormous that light takes about 100,000 years just to cross it, and used it as a unit of measurement, you would need to stack about 3,000 of them end to end to span the Boötes Void. 3,000 Milky Ways placed in a line. That is the scale of one void, and this is not even the one we live in. What made the Boötes Void so shocking was not just its size, it was the absence inside it. When Kirshner's team surveyed the region, they expected to find roughly 2,000 galaxies. They found about 60, not 2,000 minus a few hundred, not even a quarter of the expected number. 60. In a region of space where, based on the cosmic average, you would expect thousands of galaxies spread across hundreds of millions of light-years, there were 60 detectable objects. The region was not underdense. It was by any reasonable standard nearly empty. Subsequent observations over the following decades refined the picture. The Boötes Void is not, strictly speaking, completely devoid of structure. There is a sparse, loose arrangement of a few dozen galaxies loosely distributed through its interior, arranged in something that looks vaguely like a tiny filament, a ghost of the kind of structure that dominates the universe outside the void. But compared to any comparable volume of normal space, the Boötes Void is a nearly featureless, dark, quiet expanse of almost nothing. There is something in this that is hard to articulate but easy to feel. When you look at a photograph of a galaxy, even an ordinary medium-sized galaxy like the Milky Way, there is a visual richness to it, a sense of depth and population and activity. Hundreds of billions of stars, gas clouds, dust lanes, spiral arms, satellite galaxies orbiting the periphery. Life potentially scattered somewhere in the mix. That is the populated universe, the parts we are most familiar with. The Boötes Void is the opposite of all of that. Not in a poetic sense, literally. A region about the same scale as a supercluster, which should contain a comparable richness of structure, containing instead the barest, most skeletal hint of matter. For a while, astronomers wondered whether the Boötes Void might be a composite structure, several smaller voids that had merged together over billions of years, their boundaries dissolving as the matter that defined them evacuated outward. This idea, sometimes called the void of voids concept, is consistent with how void formation works theoretically. Small voids form first from early underdensities, then grow and merge as cosmic evolution proceeds, eventually producing the large coherent structures we see today. The Boötes Void may be one of these merged structures, a region where several smaller voids coalesced into a single enormous emptiness. And here is where the Boötes Void stops being just an interesting data point and starts being a mirror. Because the KBC void, the void we live inside, is about 6 to 8 times larger than the Boötes Void in linear scale. If the Boötes Void, with its 300 million light-year diameter and its 60 galaxies where there should be thousands, represents a striking example of cosmic underdensity, then the structure surrounding us, the structure we have been calling home without knowing it, is in a different category of scale entirely. The Boötes Void is what happens when the universe makes a sizable hole. The KBC void is what happens when the universe makes a hole that dwarfs the sizable one. But before we confront that directly, there is a thought experiment that Boötes invites, one that is, I think, one of the most quietly disturbing thought experiments in all of cosmology, and it starts with a simple question. What would it be like to live inside the Boötes Void? Not in any mystical sense, but scientifically, observationally. What would the sky look like? What would the history of astronomy look like? What would a civilization arising inside the Boötes Void have concluded about the universe? The answer to that question changes rather significantly how you should feel about the civilization that actually did arise. The one that built the telescopes and wrote the equations and made the measurements. The one that, it turns out, also lives inside a void, just a bigger one. Part 6. A civilization that would never know. Imagine a planet somewhere inside the Boötes Void. It orbits a star that formed there, from gas that was always sparse, always in the interior of the emptiness, far from any of the walls and filaments that outline the void's boundaries. Intelligent life evolves on this planet. It is curious, inventive, scientifically minded. It builds instruments. It looks at the sky. For most of its history, it sees exactly what we see when we look at our own galaxy. Stars, gas clouds, spiral arms, the familiar furniture of the Milky Way. It builds an understanding of stars and stellar physics. It maps the Milky Way equivalent of its own galaxy. It discovers gravity, light, thermodynamics. It builds particle physics. It starts to wonder about what lies beyond its galaxy. And then the first serious extragalactic telescopes are built. Not in the early days of science, because the universe beyond the galaxy is not bright enough to see with simple instruments, but eventually, as technology improves. Our civilization, here on Earth, built the kind of telescopes that could detect other galaxies in the early 20th century. By the 1920s, Edwin Hubble had confirmed that the Andromeda Galaxy was a separate system, millions of light-years away. That moment was a revelation, sudden, paradigm-shifting, complete. The universe expanded overnight from a single galaxy to a cosmos of billions. Now run that same story inside the Boötes Void. When the astronomers of that hypothetical civilization build their first great telescopes and point them outward, what do they see? Almost nothing. The nearest galaxies to the Boötes Void are at its walls, which are at minimum about 100 million light-years away, and in some directions much further. With the same quality of telescope that Hubble used to detect Andromeda at 2.5 million light-years, a civilization inside Boötes would see nothing. No external galaxies, no hints of a universe beyond their own. Just darkness. They would conclude reasonably and with complete logical consistency that their galaxy was the universe. Not metaphorically, literally. The universe would appear to be one galaxy, surrounded by infinite empty space. Every cosmological model they built would be a single galaxy model. Their version of the Milky Way would be the entire cosmos. This would not be stupidity. It would not be a failure of intelligence or imagination. It would be an accurate description of what their instruments could detect. The truth would be invisible, not because they lacked the cleverness to find it, but because the truth was too far away for their light-gathering technology to reach. The physical reality of the universe would be outside their observational horizon for most of their scientific history. Eventually, and this is the really interesting part, their technology would improve. Telescopes would get bigger, detectors would become more sensitive, and at some point, perhaps the equivalent of their 1960s or 1970s, faint smudges would start appearing at the edges of their deepest survey fields, hints of structure, distant, barely detectable concentrations of light at the boundaries of what their instruments could reach. They would look like anomalies at first, like instrument artifacts. Then, as confidence grew, they would be recognized as what they are, other galaxies, hundreds of millions of light years away, impossibly remote, but real. And the conceptual revolution that followed would be so much larger than our own. Our Hubble moment was transformative, but we only had to expand from one galaxy to billions. The Boötes civilization would have to expand from one galaxy to billions simultaneously, with those billions all clustered at the edges of an enormous emptiness they had been unaware of. Their entire cosmological framework would not just need updating, it would need replacing. The structure of the universe, the void they lived in, the walls that enclosed it, would all become apparent at once, as a gestalt rather than a gradual expansion of knowledge. Now here is the question that this thought experiment is designed to ask. Is our situation fundamentally different from theirs? We know about the KBC void. We know we live inside an underdensity. We know that our local measurements of the universe are made from an anomalous position. But knowing a bias exists is not the same as fully correcting for it. Our instruments are good, but they are not infinite. Our models are powerful, but they are built on data gathered from inside a hole. The Boötes civilization was limited by how far their telescopes could see. We are limited by how representative our vantage point is. The tools are different. The epistemological trap is the same. What other features of the universe might we be systematically misinterpreting because of where we sit? What is our equivalent of their single galaxy cosmology? The reasonable, internally consistent model that turns out to be a local fact mistaken for a universal one. We will come back to this. But first, let us understand how the KBC void and structures like it actually form. Because the physics of void formation is where cosmology, quantum mechanics, and the history of the universe intersect in a way that is, genuinely, one of the most extraordinary stories in all of science. Part 7. How do you even make something this empty? The universe was not always structured. 14 billion years ago, roughly, give or take the uncertainties we're trying to correct for. While sitting inside a void, the universe was extraordinarily uniform. The temperature varied by only about 1 part in 100,000 across the entire observable cosmos. Matter was spread nearly evenly through an expanding hot, dense plasma. There were no galaxies, no stars, no voids, no filaments. Just a nearly featureless sea of particles and energy, cooling as the universe expanded. The word nearly is doing enormous work in that last sentence, because those tiny, 1 part in 100,000 variations were not nothing. They were seeds, and the story of how those microscopic seeds became the KBC void, a structure 2 billion light-years across, is one of the most remarkable chain reaction stories in the history of the physical universe. The seeds themselves originated in the earliest moments after the Big Bang, during a period called inflation. Inflation is the name given to a proposed extremely rapid expansion of the universe, many orders of magnitude faster than light, that is thought to have occurred in the first tiny fraction of the first second. During inflation, quantum fluctuations, the kind of random probabilistic jitter that is intrinsic to quantum mechanics, the uncertainty at the heart of reality at the smallest scales, were stretched to macroscopic sizes. Quantum events that would normally be relevant only at subatomic scales were blown up, literally, to cosmic proportions. And because quantum mechanics is inherently probabilistic, the fluctuations were not uniform. They created tiny variations in the density of matter and energy, some regions fractionally denser than average, others fractionally less dense. After inflation ended, those fluctuations were frozen into the fabric of the expanding universe. They are visible today in the cosmic microwave background, the afterglow of the Big Bang, as tiny temperature variations mapped with extraordinary precision by satellites like WMAP and Planck. The pattern of those temperature variations tells us almost everything about the early universe, and critically, the pattern is consistent with an origin in inflation. The fluctuations have a specific statistical character, close to what is called a scale-invariant spectrum, that matches theoretical predictions for inflationary quantum noise. Now those seeds have to grow. Gravity is the engine. In regions slightly denser than average, the gravitational pull is slightly stronger than average. Matter nearby gets pulled in. The region becomes denser. The gravity gets stronger. More matter flows in. And crucially, the opposite happens in the regions that started out slightly underdense. Matter flows away from them, toward the overdense regions. The underdense regions lose matter. They become less dense. Less matter means less gravity, which means more matter flows away, which means they become less dense still. The cosmic web forms by this mutual amplification of overdensities and underdensities, like two feedback loops running in opposite directions simultaneously, one building mountains and the other carving valleys. This process is called gravitational instability. It is the fundamental mechanism of cosmic structure formation, and it is extraordinarily slow by human standards, operating over hundreds of millions to billions of years. The large-scale structures we see today, the galaxy clusters, the filaments, the supervoids, are the product of 14 billion years of this gradual amplification. Small initial differences became large final structures, given enough time. Void formation specifically follows a beautifully simple pattern. An underdense region begins to evacuate. The matter inside it flows outward, toward the surrounding denser regions. As matter leaves, the void expands, not because space inside it is growing faster than elsewhere, but because the boundaries of the void, the walls and filaments, are being pushed outward as more and more matter accumulates in them. The void grows larger as it empties, and because voids do not have the gravitational complexity of overdense regions, there is less matter inside them to create complicated substructure. They tend to maintain their roughly spherical shape as they grow. Dark matter plays a critical role in all of this. The visible matter, the gas, the stars, the galaxies, follows the dark matter gravitational scaffolding. Dark matter does not interact electromagnetically, so it cannot radiate energy and collapse efficiently the way gas does, but it provides the gravitational wells into which gas falls, and the gravitational ridges along which gas avoids accumulating. The boundaries of voids are essentially dark matter walls, high-density regions of dark matter that have been compressed by the outflow from the void interior. The visible galaxies sit in these walls, tracing the dark matter distribution. There is also the question of scale. Small voids form first, when the density contrasts are still modest. But as time goes on and the contrasts grow, small voids merge. Two adjacent underdense regions, separated by a thin density ridge, will eventually see that ridge erode as matter evacuates from both sides. The ridge disappears, and the two voids merge into one larger void. This process has been operating for billions of years, and it explains why the largest voids today, the Boötes Void, the KBC void, are far larger than any single initial underdensity in the early universe. They are composites, accumulated emptiness, the product of merging events over cosmic time. And here is the thing that makes this cosmologically significant and directly relevant to our central question. The existence of a void as large as the KBC void is, theoretically, at the outer edge of what the standard cosmological model predicts. Not impossible, but rare. A 1 in 100, or perhaps 1 in 50 statistical fluctuation. The universe could produce a void this size given enough volume to sample, but it should not do so very often, and the fact that we happen to live inside one of these rare enormous underdensities is either a coincidence or a sign that something about our understanding of cosmic structure formation is incomplete. That tension is quietly one of the live debates in modern cosmology, but the KBC void is not just an exotic address. It is a dynamic environment. It is a physics laboratory. And what happens to light and space inside a void turns out to be genuinely different from what happens elsewhere. Different in ways that affect every measurement we have ever taken. And that brings us to the physics of nothing, which is, perhaps counterintuitively, quite a rich subject. Part 8. The physics of nothing. The common intuition about empty space is that it is passive. Nothing happens there, particles zip through it, light crosses it, but the space itself does not do anything. The void is a background, not a participant. This intuition is, at a cosmological scale, quite wrong. Voids are not static. They are not simply regions where matter decided not to show up. They are dynamic environments where the physics of cosmic expansion plays out differently than anywhere else in the universe, because the local density, or more precisely the local departure from average density, affects how space itself behaves in that region. And this has consequences for how light travels through voids and how expansion appears to proceed from inside one. Start with expansion. The universe is expanding everywhere, but not at the same rate in every region. In overdense regions, galaxy clusters, superclusters, gravity resists the expansion. Matter is dense enough that its gravitational pull partially counteracts the outward push of dark energy, slowing local expansion below the cosmic average. In underdense regions, the reverse is true. There is less gravity opposing the expansion, so the expansion proceeds faster than average. Voids expand faster than the mean cosmic expansion rate. Not dramatically faster, but measurably faster. And this has a specific consequence. If you are living inside a void and measuring the expansion rate of the universe, the local measurements you make will reflect the void's enhanced expansion rate, not the cosmic average. You will infer a higher expansion rate than actually characterizes the universe as a whole. This is directly relevant to the KBC void, and it becomes even more relevant when we look at what happens to light as it travels through a void. When light travels through a gravitational well, a dense region of space, it gets blue shifted on the way in and red shifted on the way out. These effects cancel out if the gravitational field is not changing, but the universe is expanding, which means gravitational potentials are not static. As light crosses an expanding gravitational void, the potential it is climbing out of has changed by the time it exits. It is shallower than when the light entered, so the light exits with slightly less energy than it had when it entered. This is called the integrated Sachs-Wolf effect, and it is a real, measured, observationally confirmed phenomenon. Stacked analyses of the cosmic microwave background, comparing the CMB temperature in the directions of known voids, show exactly the kind of cold spots predicted by the integrated Sachs-Wolf effect. Light loses energy crossing voids. The effect is small, fractions of a millionth of a degree in the microwave background, but it is there, and it confirms that voids affect light in measurable ways. What this means for us is that light reaching our telescopes from beyond the KBC void has already been affected by its passage through the void. The photons that carry information about distant galaxies, about their redshifts and their distances, have crossed the interior of the KBC void to reach us. Their energy has been slightly modified by that crossing. The void has placed its fingerprints on the data. There is another way in which void physics is distinctive. Because voids are regions of low density and enhanced expansion, they are also regions where dark energy dominates the local energy budget more completely than in denser regions. Dark energy, the mysterious form of energy that appears to be driving the accelerating expansion of the universe, is thought to have a roughly constant energy density everywhere. It does not cluster with matter, so in a region where there is relatively little matter, dark energy makes up a larger fraction of the total energy budget. This means that dark energy's effect on local expansion is proportionally stronger inside voids than in denser regions. This makes voids, paradoxically, excellent laboratories for studying dark energy. In a dense region, the gravitational dynamics of matter complicate any attempt to isolate dark energy's signature. But in a void, where matter is sparse and the gravitational noise is relatively quiet, dark energy's effects are cleaner, more detectable, less muddied by competing physics. This is why cosmologists in recent years have started treating voids not as the boring parts of the universe, but as precision instruments, natural experiments for measuring the properties of dark energy more cleanly than is possible in overdense regions. All of which brings us back, with increasing urgency, to the central point. We live inside a void, not just any void, but one of the largest known underdensities in the observable universe. The expansion inside it is enhanced. The light traversing it is modified. The dark energy contribution to the local physics is proportionally larger. And every cosmological measurement we have made has been filtered through these effects, carried out from inside this anomalous environment. When we measure how fast the universe is expanding, We are not measuring the universe's average expansion rate. We are measuring the expansion rate as seen from inside a structure that expands faster than average. And that difference, small as it might seem in percentage terms, corresponds to one of the most stubborn, most discussed, most unresolved problems in modern cosmology. We have been circling this problem for a while now. It is time to name it. Part 9. The Map That Changed Our Address. For most of modern cosmology, the question of where we live in the universe felt comfortably resolved. It was one of those rare areas where the hierarchy was clear, almost elegant in its simplicity. We live on a planet orbiting a star. That star sits in a galaxy, the Milky Way. The Milky Way is part of a small gravitational family known as the Local Group. That group in turn lies on the outskirts of a much larger structure once called the Virgo supercluster, later reframed into an even grander entity, the Laniakea supercluster, a vast flow-defined region containing tens of thousands of galaxies moving along filaments toward a common gravitational basin. This layered address was not speculative. It was built piece by piece over decades of observation, from early galaxy catalogues to redshift surveys to velocity field reconstructions. It appeared in textbooks, in lectures, in every introductory explanation of cosmic structure. And crucially, it felt complete. The remaining work, it seemed, was not about where we were, but about how the larger structures beyond Laniakea connected, how the cosmic web extended into even greater scales, how filaments stitched together the universe into its grand architecture. In other words, our location was treated as known, representative, a typical point from which to observe the rest of the cosmos. Then the data started to push back, not dramatically at first. There was no single moment where everything broke. Instead, there was a slow accumulation of small inconsistencies, the kind that are easy to dismiss individually, but harder to ignore collectively. In the early 2000s, as galaxy surveys expanded both in depth and completeness, researchers began to notice something subtle in the numbers. When they counted galaxies within a few 100 million light-years of the Milky Way, the totals came in slightly lower than expected, not drastically lower, not enough to immediately signal a crisis, but consistently low. At first, there were reasonable explanations: observational bias, incomplete sampling, dust obscuration in the plane of the Milky Way, uncertainties in distance measurements. All of these could plausibly skew galaxy counts. And in a field as complex as cosmology, small discrepancies are not unusual. The standard model predicts statistical variation. Not every region of the universe should look exactly like the average. But this particular discrepancy did not go away. As the Sloan Digital Sky Survey began to map millions of galaxies with unprecedented precision, the statistical noise started to shrink. Infrared surveys, which could see through the dust that obscures optical observations, confirmed the pattern. Supernova surveys, using entirely different methods to trace distances and distributions, hinted at the same thing. Independent teams, working with different datasets and different techniques, kept arriving at a similar conclusion. The local universe seemed to have fewer galaxies than it should. It is worth pausing on how unusual that is in science. When a discrepancy appears in one dataset, it is often resolved by better measurements or corrected methods. When it appears across multiple independent datasets, it begins to take on a different character. It stops being a nuisance and starts becoming a signal. That signal crystallized in 2013. In that year, 3 astronomers, Ryan Keenan, Amy Barger and Lennox Cowie, published a study that would quietly redefine our cosmic context. Instead of relying on a single type of observation, they combined deep photometric and spectroscopic surveys to measure the distribution of galaxies using K-band luminosity, a wavelength range in the near-infrared that is particularly effective at tracing stellar mass. This choice was not arbitrary. Optical light can be misleading. It is affected by dust, by bursts of star formation, by the ages and compositions of stellar populations. The K-band, by contrast, provides a more stable measure of the total stellar content of galaxies. It is less sensitive to short-term variations and more reflective of the underlying mass distribution. By mapping this K-band luminosity across large volumes of space, extending out to distances of 1 billion light-years and beyond, they were able to construct a 3-dimensional picture of how matter is distributed in our cosmic neighborhood. What they found was not a small deviation. It was a large, coherent underdensity. The region surrounding the Milky Way, extending out hundreds of millions to over 1 billion light-years, contains significantly fewer galaxies than the cosmic average. Depending on the exact radius and the dataset used, the deficit ranges from roughly 15% to as much as 50%. In some interpretations, even deeper deficits appear in certain shells. This was not a fluctuation confined to a small patch of sky. It was not an artifact of incomplete coverage. It was a large-scale structure, a genuine feature of the universe. They named it the KBC Void, and with that, our cosmic address changed. Not physically, of course. The Milky Way did not move. The local group did not shift position. But the meaning of those locations, their context within the larger structure of the universe, was fundamentally revised. What had once been considered a fairly typical region of the cosmic web was now understood to be part of a vast underdensity, a region where galaxies are systematically less common than elsewhere. To grasp the scale of this revision, it helps to compare it to the structures we thought defined our neighbourhood. The Virgo supercluster, once the benchmark for large, spans on the order of 100 million light-years. The Laniakea supercluster, a more recent and more comprehensive mapping of gravitational flows, extends to roughly 500 million light-years across. These are immense structures, containing tens of thousands of galaxies, shaping the motions of matter over vast distances, and they both sit comfortably inside the KBC Void. The void itself stretches on the order of 1 to 2 billion light-years across, not just edge to edge, but in radius from our position outward. By volume, that makes it thousands of times larger than the structures we once thought defined our cosmic environment. And perhaps most strikingly, we are not near its edge. The best current estimates place the Milky Way somewhere near the centre of this underdensity. Not in a position where we could easily see its boundaries by looking in one direction versus another, but embedded within it, surrounded on all sides by a region that is, on average, less populated than the universe at large. This is what makes the discovery so consequential. If we were near the edge of the void, we could compare directions. One side would look denser, the other emptier. The asymmetry would be obvious. But from near the centre, every direction looks broadly similar. The underdensity becomes the baseline, the normal against which everything else is measured. It is the cosmological equivalent of being born in a valley so wide that it looks flat from every direction. And that brings us back to the deeper implication. Because if our local region is underdense, then the measurements we make from within it are not sampling a perfectly representative slice of the universe. They are sampling a region with its own dynamics, its own density profile, its own gravitational environment. This matters most for one particular quantity, the expansion rate of the universe. The Hubble constant is not measured directly in the abstract. It is inferred from observations of galaxies moving away from us. We measure their redshifts, how much their light has been stretched by expansion, and their distances using a ladder of calibrated indicators. From that, we derive a rate, how fast the universe is expanding per unit distance, but that rate depends on the local environment. In an underdense region like the KBC Void, there is less matter pulling inward. The surrounding denser regions exert a net gravitational influence that effectively accelerates the outward motion of galaxies within the void. The result is a slightly higher local expansion rate compared to the cosmic mean. This is not a theoretical curiosity. It is a measurable effect, predicted by models and supported by simulations, and it provides a natural explanation for at least part of the discrepancy, known as the Hubble tension. The difference between the expansion rate measured from nearby galaxies and the rate inferred from the early universe via the cosmic microwave background. The local measurements, based on supernovae and other distance indicators, consistently yield a higher value. The early universe measurements, derived from the physics of the CMB, yield a lower one. The gap between them is small in absolute terms but statistically significant. The KBC Void offers a bridge between those two numbers. It suggests that the local measurement is not wrong, but context-dependent. It reflects the expansion rate within a specific region of the universe, a region that is expanding slightly faster than average because of its lower density. That does not fully resolve the tension. Most studies indicate that the void can account for only part of the discrepancy, but it changes the framing of the problem. It introduces a physical, observationally grounded factor that must be included in any complete explanation. And once that factor is acknowledged, the question becomes broader. If our position inside the KBC void affects the Hubble constant, what else might it affect? Distances, galaxy counts, the calibration of standard candles, the inferred distribution of matter, the constraints on dark energy. Each of these depends in some way on observations made from within our local environment. Each may carry a small imprint of that environment's deviation from the cosmic mean. None of this implies that our models are fundamentally wrong. The lambda CDM model remains remarkably successful, explaining a wide range of phenomena with a small set of parameters. The KBC void fits within that framework as a rare but allowed fluctuation, a statistical outlier, but not an impossible one. What it does imply is that our perspective is not neutral. We are not observing the universe from an average location. We are observing it from inside a structure that, by its very nature, skews certain measurements in subtle but important ways. And that realization, a quiet, technical, easy to overlook, is what transforms the question of where we live from a settled fact into an active area of research. Because now the goal is not just to map the universe, but to map our position within it with enough precision to correct for its effects. To understand not just the structures we see, but how our location within those structures shapes what we see. And that is where the story leads next. Because once you accept that our cosmic address includes a billion light-year scale void, the next question is unavoidable. What happens when you measure the universe from inside a hole, and only later realize you were standing in one all along? Part 10. The local hole. Let us do the visualization properly. Let us actually trace what the KBC void looks like, going step by step from where we are outward, so that its scale settles in as a physical reality rather than an abstract number. You're here on Earth. The Earth is one of 8 planets orbiting the Sun. The solar system, including the distant Oort cloud at its outer edge, extends perhaps a couple of light-years in radius. The nearest star, Proxima Centauri, is about 4.2 light-years away. The Milky Way, our galaxy, contains somewhere between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. In the grand scheme, the Milky Way is one galaxy, large by some standards, but not exceptional. Around the Milky Way orbit a few dozen smaller satellite galaxies, the Large and Small Magellanic Clouds being the most prominent. The Milky Way and its satellites, along with the Andromeda Galaxy and its satellites, and about 50 other smaller galaxies, form the local group, a gravitationally bound collection of galaxies about 10 million light-years across. Beyond the local group, we are part of the Virgo supercluster, centered on the massive Virgo cluster about 50 million light-years away. The Virgo supercluster itself is just one lobe of the larger structure called Laniakea, a supercluster roughly 500 million light-years across that includes thousands of galaxies and the mass of approximately 100 million billion suns. Laniakea is the largest structure that can be defined by the coherent flow of galaxies toward a common gravitational attractor, the great attractor region at its center. And all of that, every galaxy mentioned above, every star in every galaxy, every piece of structure from the Milky Way to the edges of Laniakea sits inside the KBC void. Now go to the void's boundaries. The walls that define the KBC void are regions of enhanced galaxy density, filaments and sheets in the cosmic web that surround the underdensity and mark its edges. These walls are hundreds to thousands of megaparsecs away. 1 megaparsec is about 3.26 million light-years. The KBC void extends roughly 3 to 500 megaparsecs in radius, in some surveys, which corresponds to roughly 1 to nearly 2 billion light-years. The walls at its boundary, the overdense regions that represent the outside of the void, are a billion or more light-years away. Between here and those walls, the galaxy density is consistently below the cosmic average, not uniformly empty, not approaching the emptiness of the Boötes Void in the most extreme sense, but measurably, consistently underdense across the entire intervening volume. The entire structure that we would call our cosmic neighborhood is, in a statistical sense, a below-average sample of the universe. How rare is this? This is where the discussion gets appropriately uncertain, because the answer depends on exactly which version of the standard cosmological model you compare against, and on exactly how deep and how wide you define the underdensity to be. Some analyses suggest it is a roughly 1 sigma fluctuation, the kind of thing you might expect to encounter in perhaps a third of comparable volumes. Other analyses suggest it is closer to a 2 sigma or even 3 sigma event. the kind of fluctuation that would occur in only a few % of comparable volumes. The truth is somewhere in that range, and the uncertainty itself is scientifically meaningful. It reflects the fact that we are still in the early stages of correctly characterizing the void's extent and depth. What is not in serious dispute is that the underdensity is real, that it is large, and that we are inside it. The debate is about the magnitude of the effect and about its cosmological consequences. And the most significant of those potential consequences is one that connects our humble cosmic address to one of the most well-known ongoing crises in modern physics. The cosmological principle, the assumption that the universe is, on large scales, homogeneous and isotropic, is the bedrock of standard cosmology. The KBC void does not by itself disprove the cosmological principle, because the principle applies on scales of roughly 3 to 400 megaparsecs and above, and whether the KBC void represents a genuine violation or merely a large but statistically permissible fluctuation is still being examined. But it introduces a caveat, a tension, a wrinkle. A structure this large, this underdense, in a universe that is supposed to smooth out into homogeneity at large scales, is at best an uncomfortable fit with simple versions of the cosmological principle. At worst, it is evidence that the universe is less uniform than our models assume, even at the scales where uniformity should have kicked in. Our cosmic address is not typical, and what that means for the measurements made from inside it is, right now, a live and contested scientific question. Part 11. The universe expands at two speeds. There is a number at the centre of modern cosmology. It has a symbol, h subscript 0, h0, and a name, the Hubble constant. It describes how fast the universe is expanding. Specifically, it tells you how fast a galaxy is receding from us for every megaparsec of distance. At a distance of 1 megaparsec, about 3.26 million light-years, a galaxy is receding at 80 kilometers per second. At 2 megaparsecs, twice as fast. At 10 megaparsecs, 10 times as fast. The Hubble constant is the heartbeat of the expanding universe, the master parameter from which cosmic expansion, cosmic age, and the fate of everything follows. For decades, astronomers struggled to pin down the value of H0 precisely. Different methods gave different answers, and the uncertainties were large enough that the disagreements were not alarming. But as instruments improved and measurements became more precise, something alarming emerged. The different methods were not converging on the same answer. They were converging on different answers, with uncertainties that no longer overlapped. There are two primary approaches to measuring H0. The first is the local distance ladder, a chain of measurements starting with parallax measurements of nearby stars, moving to Cepheid variable stars in nearby galaxies, then to type Ia supernovae in distant galaxies, each rung of the ladder extending further into the universe. This approach gives a value of roughly 73 kilometers per second per megaparsec, with an uncertainty of about 1 to 2%. The second approach uses the cosmic microwave background, the afterglow of the Big Bang, combined with the standard cosmological model, to infer what the expansion rate should be today based on the early universe's properties. This approach gives a value of roughly 67 kilometers per second per megaparsec, 73 versus 67, a difference of about 8 to 9%. And the statistical significance of that disagreement, given the measurement uncertainties, has grown over the years to approximately 5 sigma. In science, 5 sigma is the threshold conventionally required to claim a discovery. A 5 sigma discrepancy between two measurements of the same physical quantity is not a rounding error. It is not a systematic bias that will quietly resolve with slightly better data. It is a real, persistent, statistically robust tension that demands an explanation. This is the Hubble tension. It is arguably the most important unsolved problem in observational cosmology, and one of the serious, peer-reviewed, actively investigated potential explanations is our position inside the KBC void. The mechanism is precisely what we outlined in the previous section. If we are inside a large underdensity, and if underdensities expand faster than the cosmic mean, then the local distance ladder measurements are systematically biased upward. They are measuring the expansion of a below-average density region of the universe, not the universe as a whole. The void's enhanced expansion makes the local universe look like it is expanding faster than the CMB-based prediction, because the CMB prediction reflects the global average, not the local void's enhanced rate. How much of the Hubble tension can be explained this way? This is where the debate currently sits. Some studies find that the KBC void underdensity is sufficient, or nearly sufficient, to account for the entire tension. Others find that the effect is real but can only explain perhaps half to two-thirds of the discrepancy, leaving a residual tension that needs another explanation. The honest answer is that it is not yet resolved. The void's contribution to the Hubble tension is a real effect, physically motivated, observationally constrained, and taken seriously by mainstream cosmologists. Whether it is the primary explanation or a contributing factor among several is an open question. What is significant for our central story is what this implies. One of the most important numbers in cosmology, the rate at which the universe is expanding, may be systematically biased because of where we are taking the measurement. Not because our instruments are faulty, not because our physics is wrong, but because we are inside a void, and measuring the universe from inside a void is not the same as measuring it from a typical location. Every cosmology textbook written in the past 50 years quotes a Hubble constant. Every calculation of the universe's age, every model of its future, every constraint on dark energy derived from local expansion data used that number. And that number may be the expansion rate of our local void, not the universe at large. The asterisk is already on every map. The question is how big the correction turns out to be. Part 12. The dangerous implication. Let us be precise about what is and is not being claimed here, because this is the part of the story where it is most important to resist the pull toward overstatement, but also most important not to understate the genuine significance of what we are dealing with. The KBC void is real. The fact that we live inside a large local underdensity is at this point multiply confirmed by independent methods. The fact that this underdensity affects local expansion measurements is physically well motivated and consistent with the observed Hubble tension. None of this is fringe science. None of this challenges the Big Bang, or the existence of dark matter, or the reality of dark energy. The framework of modern cosmology remains sound. What the KBC void does challenge is the assumption of representativeness, the assumption that our local measurements of the universe are typical measurements of the universe, the assumption that the physics we observe locally, the expansion rates we measure locally, the galaxy distributions we map locally, are close to the cosmic average. There are three broad interpretive frameworks for what the KBC void means. The first is that it is a statistical fluctuation within the standard model. Unusual, but not impossible, a 1 in 50 or 1 in 100 event, the kind of rare circumstance that has to be true somewhere and happened to be true here. On this view, the KBC void is cosmologically interesting but not foundationally threatening. Our measurements are biased, we correct for the bias as best we can, and the standard model continues to describe reality well. The Hubble tension might be partially explained by the void effect, with any remaining discrepancy resolved by other physics. This is probably the most common view among working cosmologists today. The second interpretation is that the KBC void is the primary explanation of the Hubble tension. On this view, the tension is not a sign of new physics beyond the standard model. It is a measurement artifact, a consequence of our position inside an underdensity that inflates local expansion measurements. Under this interpretation, the universe is actually expanding at 67 km per second per megaparsec, as the CMB predicts, and the higher local values reflect the void's enhanced expansion rate, not the true cosmic mean. Some published studies support this position. Others find it requires a void underdensity somewhat larger than the best current observational constraints allow, though the constraints themselves carry uncertainty. The third interpretation is the most radical and the most speculative. It says that the existence of a void as large and as deep as the KBC void, sitting in a universe that is supposed to be statistically homogeneous at these scales, suggests that the cosmological principle itself needs modification, that the universe is not as uniform as the standard model assumes, even on the scales where uniformity was supposed to be guaranteed, that the initial conditions of the Big Bang, or the physics of structure formation, or something else entirely, produced a universe with more large-scale variance than our models predict. This interpretation, if correct, would require modifications to the foundational assumptions of cosmology. It is not well supported by current evidence in a strong sense, but it cannot be ruled out, and some researchers take it seriously as a possibility. What all three interpretations have in common is the recognition that our position inside the KBC void is not a cosmologically neutral fact. It changes things, it biases measurements, it introduces uncertainties, and it forces the question, if we knew we were inside a void, if we'd always known it, how would we have built cosmology differently? What would the equations look like? What assumptions would we have questioned earlier? We did not always know. We built the entire edifice of modern cosmology from inside this hole, without knowing it was a hole. And now that we know, the question is whether the edifice needs repair, reinforcement, or reconstruction. The answer, almost certainly, is some of each. And that process of correction is going to be one of the defining projects of cosmology in the coming decades. But here is what I want you to hold for a moment. Not the technical question of which interpretation is correct, not the measurement uncertainties, the human reality of it. Every astronomer who ever lived, every equation ever written about the expanding universe, every age estimate of the cosmos, every model of cosmic history, all of it was constructed from a vantage point inside an anomaly. The universe was being measured from a non-representative location by inhabitants who did not know they were non-representative. The science is not wrong, but it is, in some subtle and real sense, local. It is a description of the universe as seen from inside a void. And the obvious question that raises is, what does the universe look like from outside it? Part 13. The universe from outside the void. We cannot physically leave the KBC void, not in any human time frame, not with any technology we possess or could reasonably imagine possessing within the next several centuries. The void is 2 billion light-years across, at the speed of the fastest spacecraft humanity has ever launched. Voyager 1, which has been travelling away from Earth since 1977 and is currently moving at roughly 17 kilometers per second, it would take approximately 35 trillion years just to cross a single light-year. A single one. The void contains 2 billion of those light-years. We are, for all practical purposes, not just currently located at our position in the cosmic web. We are permanently located here. The KBC void is not a neighbourhood we are passing through. It is the neighbourhood. It is the only neighbourhood our species has ever known or will ever know, at least in any time frame that connects to anything we would recognise as human civilization. And yet, that physical constraint does not mean we are trapped in ignorance. Because science has always done something remarkable when faced with the walls of the physically reachable. It uses mathematics, logic, and observation to construct a picture of what lies beyond them. We cannot send a probe outside the KBC void. We cannot relocate our telescopes to one of the dense filaments or walls that mark its boundaries. But we can ask, carefully and rigorously, what an observer sitting in one of those walls would see when they look toward us. We can model the view from outside. We can calculate the difference between their measurements and ours. And when we do, the answer is illuminating in ways that go well beyond academic curiosity. Start with the simplest and most direct consequence. An external observer, someone sitting in a region of average or above average density, in one of the filaments or walls surrounding the KBC void, would see our local universe with more galaxies per unit volume than we do. Their surveys of the nearby cosmos, if pointed in our direction, would return lower galaxy counts in the void region and higher counts in their own denser neighbourhood. Their measurements of luminosity density, the total light output per unit volume of space, would be higher because they are surrounded by more galaxies. The sky, in a sense, would be brighter from their perspective, not because any individual galaxy is more luminous, but because there are simply more of them per cubic megaparsec. Their calibration of standard candles, the objects astronomers use as reference points to build distance ladders, might also differ in subtle but meaningful ways. Type Ia supernovae, the primary rung of the local distance ladder, are calibrated using host galaxies in the local universe. If those host galaxies are preferentially located in an underdense environment, their properties might differ slightly from the cosmic average. Subtle differences in the stellar populations, the metallicity of the environments, the ages of the stellar systems that produce the supernovae. These are small effects, contested in the literature and not yet confirmed as a meaningful source of systematic bias. But they are plausible, and an external observer with a distance ladder calibrated in a denser, more representative region might find a slightly different result when applying it to the same set of distant supernovae. More significantly, and this is the part that connects most directly to the Hubble tension, The expansion rate an external observer measures locally would be lower than ours. They are not inside a void. The dark energy-dominated enhanced expansion that characterizes the interior of the KBC void would not be inflating their local expansion rate estimates. Their measurements would reflect a density closer to the cosmic average and an expansion rate closer to the cosmic average. Using the same methods we use, they would likely measure an expansion rate somewhere closer to 67 km per second per megaparsec, the value derived from the cosmic microwave background, rather than the 73 that our local distance ladder consistently returns. This is an important point because it means the Hubble tension is not simply a discrepancy between two measurements of the same physical quantity. It may be, at least in part, a discrepancy between two measurements made from different environments, one from inside a void, one from the very early universe before structure had formed. The CMB measurement is, in a sense, the universe measuring itself from a state of near-perfect uniformity, before any voids or filaments existed. Our local measurement is the universe being measured from one of the most anomalous environments in the present-day cosmic web. These two measurements need not agree. They may be measuring the same underlying physics, but from positions so different in terms of local density that the local physics genuinely differs between them. This is a testable prediction, and that testability is what elevates it from speculation to science. As surveys extend to greater distances, encompassing not just the interior of the KBC void, but also the denser walls and filaments beyond it, the measured expansion rate should change. It should transition, gradually but measurably, from the locally elevated value we see in the void interior toward the global CMB value, as the survey volume grows large enough to include representative portions of the universe beyond the underdensity. Some researchers already report hints of exactly this pattern. Studies that measure how the inferred Hubble constant shifts as a function of the redshift depth of the survey, how far out the measurement reaches, find a suggestive trend in the expected direction, with the local value declining slightly as the survey depth increases and begins to sample beyond the void. The data are not yet clean enough or deep enough to be definitive, but the signature is there. Future surveys, the Vera Rubin Observatory, the Euclid Satellite, the Nancy Grace Roman Space Telescope, will push deep enough to characterize this transition with real precision, and what they find will either confirm or challenge the void explanation for the Hubble tension. There is a deeper point here about what cosmology fundamentally is and what it is actually trying to do. Cosmology aims to describe the universe as a whole, its composition, its geometry, its origin, its eventual fate. The cosmological principle, the assumption of large-scale homogeneity and isotropy, was not just a convenient simplification. It was the philosophical justification for the entire project of using local measurements to make universal claims. If the universe is the same everywhere at large scales, then measuring it from here is as good as measuring it from anywhere else. Local becomes universal. A sample of one location is a representative sample of all locations. But if our local measurements are not representative, if we are sampling from an underdense region rather than the typical universe, then that justification is compromised. Not completely wrong, but incomplete. The extrapolation from local to universal is still possible, but it requires a correction. And without that correction applied, we are not measuring the universe. We are measuring our region of the universe and calling it the universe, which is a subtle but consequential category error. The metaphor that captures this most cleanly is topography. Imagine you're trying to determine the average elevation of the Earth's entire surface. You have a perfect altimeter. Your GPS is flawless. Your mathematical analysis is impeccable. Now imagine you're conducting this measurement from the bottom of the Mariana Trench, the deepest point on the planet's surface, nearly 11 kilometers below sea level. Your instrument reads the correct elevation for where you are. But where you are is one of the most extreme outlier points on the entire surface of the Earth. The average surface elevation of Earth is actually about 840 meters above sea level. Your reading, approximately negative 11,000 meters, is not wrong. It is just spectacularly unrepresentative. To get the true average, you need to either sample from many locations across the surface or apply a known correction for the fact that you are starting from one of the lowest points. If you skip that step, your average will be wildly off, and no amount of measurement precision will fix the problem, because the problem is not precision, it is position. We are standing in the Mariana Trench of the cosmic density field, not as dramatically displaced from the mean, as the deepest ocean trenches from the mean surface elevation, but displaced in the same structural sense. Our instruments work, our physics is sound, our mathematics is correct. But we are at the bottom of a gravitational deficit, a region where the matter density is 15 to 50% below the cosmic average, measuring outward from one of the emptier regions in the observable universe. The correction for our position is not zero, it is not negligible. It may in fact be the resolution to the most important unresolved problem in modern observational cosmology. And here is the thing that makes this even more compelling than just the Hubble tension. The Hubble tension is the most famous consequence of our position, but it is likely not the only one. The KBC void touches something larger, a pattern of anomalies scattered across the large-scale universe that may not be coincidental. There is the CMB cold spot, that anomalously cold region of the cosmic microwave background in the direction of Eridanus, cold in a way the standard model struggles to explain without invoking a large supervoid along the line of sight. There is the Eridanus supervoid itself, a structure potentially comparable to the KBC void in scale, found in the direction of that cold spot. There are large-scale anomalies in the distribution of structure, hints that the universe at its largest scales may be slightly less uniform than our standard model comfortably accommodates, and at every one of these anomalies, the fingerprints of voids are present, not proven, not definitively established as the cause, but there, consistent, persistent across independent analyses, which raises the possibility that what we are slowly discovering is not just one unusual feature of our local environment, but a broader truth about the universe at its larger scales. A universe that may be somewhat stranger, somewhat less smooth, somewhat more structured by emptiness than our models have assumed. The KBC void may not be an isolated oddity. It may be one visible piece of a pattern that the next generation of surveys is only beginning to reveal. Part 14. The cold spot and the bigger pattern. In 2004, the Wilkinson Microwave Anisotropy Probe delivered what was, at the time, the most precise full-sky map ever made of the cosmic microwave background. This faint radiation is not just background noise. It is the oldest light we can see, released when the universe was only about 380,000 years old. Before that moment, the universe was an opaque plasma, a dense fog of charged particles constantly scattering photons. But as it expanded and cooled, protons and electrons combined into neutral hydrogen, and suddenly light could travel freely. The CMB is that first light, stretched by cosmic expansion over billions of years into microwaves, now filling the universe almost perfectly evenly at a temperature of about 2.7 Kelvin. What makes the CMB so powerful is not its uniformity, but its imperfections. Across the sky, it varies by about 1 part in 100,000. Tiny fluctuations that represent the original density differences seeded in the early universe. These slight variations are the fingerprints of everything that came after: galaxies, clusters, filaments, and crucially, the vast voids between them. When cosmologists analyze the CMB, they are effectively reading the initial blueprint of the cosmos, a map of where matter would eventually accumulate and where it would thin out. For the most part, the WMAP data match theoretical predictions with astonishing precision. The fluctuations followed the expected statistical distribution, reinforcing the standard model of cosmology, the LCDM framework, where dark energy and dark matter govern the universe's evolution. But there was one feature that stood out. In the direction of the constellation Eridanus, astronomers found a region that didn't behave like the rest. It was colder than it should have been, not by a small margin, but enough to stand out as a statistical anomaly against the otherwise smooth backdrop. This feature came to be known as the cold spot. It spans about 5 degrees across the sky, which might not sound like much until you realize that the full moon is only about half a degree wide. That means the cold spot is roughly 10 times larger than the moon in apparent size. It is not just a minor fluctuation, it is a large, coherent region where the temperature dips significantly below the average. Subsequent observations by the Planck spacecraft confirmed its existence with higher precision, ruling out the possibility that it was an artifact of instrumentation or noise. Whatever the cold spot is, it is real. The question, then, is what could produce such a feature. One of the most compelling explanations connects directly to the physics of voids. When photons from the CMB travel through the universe on their way to us, They pass through regions of varying gravitational potential. In a universe dominated by dark energy, these potentials evolve over time. If a photon passes through a large underdense region, a supervoid, it experiences a subtle energy shift due to what is known as the integrated Sachs-Wolf effect. As the photon falls into the gravitational well of a region and then climbs out, the expansion of the universe changes the depth of that well during the journey. In a void where gravity is weaker and dark energy dominates, the net effect is that the photon loses a tiny amount of energy, emerging slightly cooler than it entered. If there were a sufficiently large void between us and the surface of last scattering, aligned with the cold spot, it could imprint exactly this kind of temperature anomaly onto the CMB. That idea remained speculative for years, until observational data began to hint at something intriguing. In 2015, researchers analysing data from the Dark Energy Survey reported evidence for a massive underdense region in the direction of the cold spot. This structure, now referred to as the Eridanus supervoid, was estimated to span roughly 1.8 billion light-years and to have a density about 20% below the cosmic mean. That scale is not trivial. A void approaching 2 billion light-years in size is comparable to the largest known underdensities in the observable universe, including the KBC void that surrounds our own galaxy. The implication is immediate and profound. If the Eridanus supervoid is real and properly characterized, then the cold spot is not just a random fluctuation, it is a direct observational consequence of large-scale structure. It would mean that voids are not merely empty gaps between filaments, but active participants in shaping what we see when we look at the universe's oldest light. But the situation is not so simple. While the presence of the Eridanus supervoid aligns well with the cold spot in both direction and approximate scale, detailed calculations have raised an issue. The integrated Sachs-Wolf effect produced by a void of that size and depth appears to account for only a portion of the observed temperature decrement. Estimates suggest it might explain somewhere between 30 and 50% of the cold spot's anomaly. The remaining signal, the deeper-than-expected cold region, does not have a clear explanation within the standard model. This leaves cosmologists in an uncomfortable position. On one hand, the cold spot could be a rare statistical fluctuation, an unlikely but not impossible outlier in the random distribution of CMB anisotropies. Given the vast number of independent regions across the sky, even improbable events can occur somewhere. On the other hand, the alignment with a massive supervoid suggests a physical mechanism is at work, but one that does not fully account for the data. And beyond that lie more speculative possibilities, ranging from non-standard inflationary physics to exotic scenarios involving topological defects or even interactions with other regions of spacetime. None of these ideas have been confirmed, and most remain firmly in the realm of hypothesis. What matters for our central story is not which explanation ultimately proves correct, but what the existence of the cold spot and the Eridanus supervoid together imply. They suggest that structures on the larger scales, hundreds of millions to billions of light-years, are not passive or negligible. They actively shape the signals we use to understand the universe. The cosmic microwave background, often treated as a pristine snapshot of the early universe, is in fact filtered through billions of years of large-scale structure before it reaches us. Voids, in particular, act as subtle lenses, modifying the energy of photons in ways that can leave detectable imprints. This brings us back to the KBC void. If one supervoid can leave a measurable imprint on the CMB, then what does it mean that we are embedded inside another one of comparable scale? The difference, of course, is that the Eridanus supervoid lies between us and the CMB, affecting photons passing through it, while the KBC void surrounds us, affecting how we observe everything beyond it. It influences galaxy counts, luminosity densities, and potentially even the local measurement of cosmic expansion. It is not just a feature we observe, it is the environment from which all our observations are made. Taken together, these structures hint at a universe that is more complex at the larger scales than the simplest interpretation of the cosmological principle would suggest. The principle states that, on sufficiently large scales, the universe is homogeneous and isotropic, essentially the same in all directions and locations. But the presence of multiple billion light-year scale underdensities, each with measurable observational consequences, raises the question of how quickly that homogeneity is actually reached. If the scale of significant structure extends farther than expected, then our local region may not be a fair sample of the universe as a whole. This does not mean the standard model is wrong. LCDM has passed an extraordinary range of tests, from the detailed structure of the CMB power spectrum to the distribution of galaxies and the expansion history of the universe. But it does mean that the model must accommodate the existence of these large, rare fluctuations, and that we must be careful about how we interpret observations made from within them. The cold spot, the Eridanus supervoid, and the KBC void are not isolated curiosities. They are data points in a larger pattern, one that may still be only partially mapped. There is also a deeper, almost philosophical implication to all of this. When we look at the cosmic microwave background, we are seeing the universe as it was nearly 14 billion years ago. But we're not seeing it directly. We're seeing it through the intervening structure of the universe as it has evolved since then. Every photon has taken a path shaped by gravity, by expansion, and by the distribution of matter and emptiness it encountered along the way. In that sense, our picture of the early universe is always mediated by the late universe. And if the late universe contains structures as large and influential as supervoids, then those structures are part of the story we are trying to reconstruct. What the cold spot ultimately represents, then, is not just an anomaly to be explained, but a reminder of the limits of our perspective. It is a signal that something along the line of sight, something vast and diffuse and difficult to map, has altered the light we use to probe the deepest past. Whether that something is fully understood within existing physics or points toward new phenomena remains an open question. But either way, it reinforces the central idea. We do not observe the universe from nowhere. We observe it from somewhere very specific, and that location matters. And when we extend that idea forward in time, the implications become even more striking. Voids are not static features, they evolve. As dark energy continues to drive the accelerated expansion of the universe, underdense regions grow faster than dense ones. Matter flows out of voids into filaments and clusters, leaving the voids increasingly empty. Over billions and trillions of years, this process continues, amplifying the contrast between structure and emptiness. Eventually, if current models are correct, the universe will reach a state where these voids dominate almost entirely. Galaxies outside our local group will recede beyond the cosmic horizon, becoming permanently unobservable. The large-scale structure we see today will thin out, leaving isolated islands of matter surrounded by vast expanses of near-perfect emptiness. In that far future, observers, if any remain, will have an even more limited view of the cosmos than we do now. They will not see the cosmic web. They will not see the relic radiation of the Big Bang. They will see only their local environment, embedded in a universe that appears empty and static. In a sense, that future mirrors the thought experiment of a civilization inside a void. Their cosmology would be shaped by what they can observe, and what they can observe would be shaped by where they are. The difference is that, in the far future, that limitation would not be temporary. It would be fundamental, imposed by the expansion of space itself. So when we ask what happens to voids as the universe ages, the answer is not just a matter of structure formation, it is the long-term trajectory of the cosmos. Voids grow, they merge, they come to dominate, and in the end, the universe approaches a state where emptiness is not just the majority of volume, but effectively the entire accessible reality. The galaxies, the clusters, the filaments, all of it becomes a kind of transient scaffolding, a temporary structure suspended within an ever-expanding background of nothing. That is the direction the data points toward, and it is here that the cold spot, the Eridanus supervoid, and the KBC void converge into a single idea. They are not anomalies in an otherwise smooth universe. They are glimpses of the underlying geometry that defines it, a geometry in which emptiness is not the absence of structure but the structure itself. Part 15. The future. When the void wins. The universe is not a finished thing. It is not a stable structure sitting in balance. It is a process, and not a gentle one. From its first fractions of a second, it has been evolving in a single, irreversible direction. Not toward complexity, not toward richer structure, but toward something quieter, simpler, and far more extreme: emptiness. That can feel counterintuitive at first because everything we see suggests the opposite. Galaxies form, stars ignite, planets condense, life emerges. It looks like a universe building itself layer by layer into something intricate and meaningful. But zoom out far enough, not just in space but in time, and a different pattern appears. Structure is not the destination. Structure is a temporary phase, like foam on the surface of a wave. The long-term trajectory is the removal of that foam, until only the flat, empty ocean remains. The force driving that transition has a deceptively simple name: dark energy. It is one of the most important components of the universe, and also one of the least understood. We do not know what it is in a fundamental sense. We do not know why it exists. But we know what it does, and what it does is enough to determine the fate of everything. Dark energy behaves in a way that breaks intuition. Almost every form of energy we're familiar with, matter, radiation, even hot gas, becomes more dilute as space expands. Imagine spreading a fixed amount of paint across a growing canvas. The more the canvas stretches, the thinner the paint becomes. That is how ordinary energy works. Its density drops as volume increases. Dark energy does not follow that rule. As space expands, the density of dark energy remains roughly constant. It does not thin out. It does not weaken. Instead, more space simply means more dark energy in total. The universe grows, and the amount of dark energy grows with it. This leads to a strange and powerful consequence. Early in the universe, when matter was densely packed, gravity dominated. Gravity pulled matter together, amplifying tiny fluctuations into galaxies, clusters, and the vast filaments of the cosmic web. That is why structure exists at all. But as the universe expanded and matter spread out, its density dropped. Dark energy, remaining constant, slowly became the dominant component. Today, it makes up about 68% of the total energy content of the universe. Matter, everything from galaxies to atoms, accounts for less than a third, and that fraction is shrinking with time. Dark energy does one thing relentlessly. It accelerates the expansion of space, not just allowing the universe to grow, but causing that growth to speed up. The distances between galaxies increase faster and faster as time goes on, and this acceleration has consequences that ripple through every level of cosmic structure. In regions where gravity is strong, inside galaxies, inside clusters, expansion does not win. The gravitational binding is enough to hold things together. The Milky Way will not be torn apart by cosmic expansion. Neither will the Andromeda Galaxy. In fact, the Milky Way and Andromeda are on a collision course and will merge in a few billion years, forming a single larger galaxy. But beyond those tightly bound systems, the story changes. Galaxies that are not gravitationally tied to each other are being carried apart by the expansion of space itself, and as that expansion accelerates, the separation grows faster and faster, until something remarkable happens. The distance between two galaxies can increase faster than light could ever travel between them. This does not violate the laws of physics, because nothing is moving through space faster than light. Instead, space itself is expanding, stretching the distance between objects. The effect is the same, though. Light emitted from one galaxy can no longer reach another if the space between them expands too quickly. This defines a boundary, the cosmic horizon. It is not just the edge of what we can currently see, but the edge of what we can ever see, even in principle. Beyond that horizon, events are permanently cut off from us. Right now, that horizon lies at a distance of roughly 46 billion light-years. But here is the part that quietly shifts everything. The horizon is not fixed. Because expansion is accelerating, the boundary is effectively shrinking in terms of what remains reachable. Galaxies that are currently visible will not always be. Over the next tens of billions of years, more and more galaxies will cross that horizon. Their light will stretch, redshift, and fade until they disappear from view entirely. One by one, the large-scale structure of the universe will blink out. If you could stand in the Milky Way tens of billions of years from now and look out into space, the night sky would not look like it does today. The distant galaxies, the faint smudges captured in deep field images, would be gone. Even large neighbouring clusters would no longer be visible. The only galaxies remaining in view would be those gravitationally bound to us. The local group merged into a single structure. Everything else will have slipped beyond the horizon, not destroyed, not gone, but unreachable. The observable universe will have collapsed, not physically, but informationally, into a much smaller region. This process does not stop there. It continues steadily over far longer timescales. The cosmic web, the vast network of filaments and walls that connect galaxies across hundreds of millions of light years, depends on gravity maintaining those connections. But as expansion accelerates, those connections weaken. Matter either falls inward into local gravitational wells or is carried outward into the expanding voids. The filaments thin, the walls stretch, the structure begins to unravel. What replaces it is not chaos, but isolation. Instead of a connected web, the universe becomes a collection of gravitational islands, clusters or merged galaxies, each bound internally but separated from all others by distances that grow without limit. Between those islands, the voids expand. This is where the story loops back to where we began. Voids are not just empty regions between structures. They are the dominant environment of the universe, and they are the fastest growing part of it. Inside a void, there is very little matter to slow expansion. Dark energy acts almost unopposed. The void stretches faster than denser regions, becoming larger and emptier over time. The KBC void, the immense underdensity that contains the Milky Way, is already an example of this process in motion. Its interior is less dense than average. Its expansion rate is slightly higher. Over billions of years it will grow, its boundaries pushing outward as matter drains into surrounding filaments or is pulled away by expansion. We are not living in a static structure. We are living inside something that is actively evolving toward emptiness. Now extend that process forward, far beyond the lifetime of stars. Stars do not last forever. Even the longest-lived red dwarfs, which can burn for trillions of years, will eventually exhaust their fuel. Star formation itself will slow and eventually cease as the raw material, a cold gas, is used up or locked into stellar remnants. After tens of trillions of years, the universe will enter what is sometimes called the degenerate era. The bright active phase of stars will be over. What remains will be stellar remnants, white dwarfs, neutron stars, black holes, and cold dark objects drifting through space. But even this is not the final state. If certain theories in particle physics are correct, protons themselves are not perfectly stable. Over extremely long timescales, perhaps 1034 years or more, they may decay into lighter particles. This would mean that even ordinary matter, the atoms that make up everything familiar, would gradually disintegrate. Black holes, often imagined as eternal, are not truly permanent either. Through a process known as Hawking radiation, they slowly lose mass, emitting particles over time. For stellar mass black holes, this process takes on the order of 1067 years. For the supermassive black holes at the centers of galaxies, it can take up to 100 years. Eventually, even they evaporate. What remains after that is difficult to picture, because it is so far removed from any environment we have experienced. A thin bath of low-energy radiation. Elementary particles spread across an enormous, ever-expanding volume. Temperatures approaching absolute zero. No gradients, no structure, no ongoing processes. This is what physicists call heat death, a state of maximum entropy, where energy is evenly distributed and no work can be extracted from any system. It is not an explosion or a collapse. It is a fading, a smoothing out, a final leveling. And in a very literal sense, it is the ultimate void. Not a void like the KBC void, which still has galaxies, still has structure, still has dynamics, but a void in the most complete meaning of the word, a universe where the distinction between something and nothing has nearly disappeared. Seen from this perspective, the era we are living in is extraordinarily brief and extraordinarily special. The universe began in a nearly uniform state, with tiny fluctuations. Those fluctuations grew into structure, into galaxies, stars, and planets. And for a window of time, that structure became complex enough to support chemistry, biology, and conscious observers. But that window is temporary. It is bounded on one side by the early universe, before structure formed, and on the other by the deep future, after structure dissolves. We exist in the middle of that arc, and the presence of large voids like the KBC void is not a side detail in that story. It is a preview of the direction everything is heading. Voids are regions where the future has, in a sense, arrived early. They are less dense, more dominated by dark energy, more rapidly expanding. They are closer to the end state than the dense regions around them. As time goes on, more of the universe will come to resemble them. The filaments will fade, the clusters will isolate, the distances will stretch, and the overall character of the universe will shift, slowly but inexorably toward emptiness. This does not mean that anything meaningful is being erased in the present. The timescales involved are so vast that they dwarf human history, human civilization, even the lifetime of stars. But it does mean that the universe has a direction, and that direction is not toward greater complexity, but toward simplicity, toward stillness, toward the kind of quiet that cannot be broken. And if you step back and look at the full arc, from the first fluctuations after the Big Bang, to the formation of the cosmic web, to the growth of voids, to the eventual dissolution of all structure, a pattern emerges that reframes everything. The galaxies, the stars, the luminous structures we associate with the universe are not the baseline. They are the exception. They are the brief scaffolding that forms under the right conditions and then fades. The voids are the baseline. They are the dominant geometry from the beginning, and they will be the dominant geometry at the end. We are not living in a universe filled with matter punctuated by empty spaces. We are living in a universe of emptiness, briefly illuminated by matter. Part 16. The asterisk on every map. We have travelled a long way from the opening statement. From the quiet second-person provocation of right now, you are sitting inside one of the largest known emptiness in the observable universe. Through the graded emptiness of the intergalactic medium, the foam-like architecture of the cosmic web, the vertiginous scale of the Boötes Void, the thought experiment of a civilization that never knew other galaxies existed, the physics of nothing, the landmark paper of 2013, the Hubble tension, the view from outside the void, the CMB cold spot, and the slow triumph of emptiness in the far future, we have arrived at the place this story was always heading. Every measurement of the universe has an asterisk, not a big alarming asterisk, not a symbol of failure or deception, a quiet epistemic asterisk, a note in fine print at the bottom of every cosmological textbook that has ever been written, waiting to be placed there once we knew enough to put it. Something like, all measurements made from within the KBC void, corrections for local underdensity pending. What does it mean for a map to have an asterisk? It means the map is accurate for what it is. It means the measurements are real, the instruments are calibrated, the mathematics is sound. But it also means the context of those measurements introduces a systematic bias that needs to be acknowledged, quantified, and eventually corrected. Our maps of the cosmos are extraordinarily detailed and extraordinarily accurate given what they are. They are maps of the universe as seen from inside a below-average density region, near the middle of a 2 billion light-year void, constructed by observers who did not know they were inside a void for most of the history of the discipline. The Hubble constant is the most famous casualty of this asterisk. But it is probably not the only one. The inferred age of the universe, derived partly from the expansion rate, may carry a small correction. The calibration of the cosmic distance ladder, built from standard candles observed in our local universe, may need adjustment for the fact that those standard candles were calibrated in an underdense environment. The constraints on dark energy, derived partly from measurements of how expansion has changed over time as seen from our location, may need to account for how the void's enhanced local expansion affected those observations. None of these corrections are likely to overturn the standard cosmological model, lambda CDM, the model of a universe with cold dark matter and a cosmological constant, has survived dozens of precision tests across wildly different observational techniques and physical regimes. It is not going to be replaced by a radically different framework because of the KBC void, but it may be refined. The values of its key parameters may shift. The confidence intervals may widen in places where they previously seemed tight, as researchers account for the systematic effects of our unusual location. And in that refinement lies something genuinely important and perhaps underappreciated, the scientific process working exactly as it should. We built models from available data. We found anomalies that the models did not explain. We traced those anomalies to a physical cause, our location inside a large underdensity. And now we're in the process of correcting for that cause, building a more accurate picture of reality by acknowledging a limitation in our perspective that we did not previously recognize. This is not a failure of cosmology. It is cosmology succeeding. Slowly, painstakingly. with the kind of intergenerational patience that the scale of the problem demands. Physicists working in the 1950s did not know about the KBC void. Physicists working in the 1980s had hints but not confirmation. Physicists working today have confirmation but not full quantification. Physicists working in the 21st century will build the surveys deep and precise enough to characterize the void completely and correct for its effects with confidence. The project is underway. What strikes me, sitting with this story in its entirety, is the human element. Every astronomer who ever lived and worked, Hubble, Zwicky, Rubin, Penzias, Wilson, Geller, Huckra, and everyone whose name we know and everyone whose name we do not, was making their measurements from inside the same hole. None of them knew it. The greatest tools of human ingenuity, the most precise instruments ever constructed for measuring the cosmos, the most sophisticated mathematical frameworks ever assembled for modelling reality, all of it deployed from an unusual non-representative corner of the universe, by a species that had no way of knowing its own address until the surveys got deep enough to show it. And the surveys finally got deep enough. 2013, a paper by 3 astronomers at the University of Hawaii, measuring the distribution of galaxies in the K-band across a wide swathe of the local universe, producing a result that said, clearly and publicly, we live inside a large underdensity. It did not make the front pages. It did not cause a crisis in the same way the Hubble tension has. But it changed, quietly and permanently, what we know about our cosmic context. There is a thing that happens in science occasionally, a kind of retrospective vertigo, when a discovery forces you to look back at an entire history of prior work and see it slightly differently. Not wrongly, the prior work was not wrong, but incompletely. The way the discovery that the Earth orbits the Sun forced a retrospective look at every astronomical observation made from the geocentric assumption. The work was not wrong, but the frame was incomplete, and once the frame was corrected, the observations fit together more coherently. The discovery of the KBC void is that kind of moment for cosmology. Not as dramatic, not as widely recognized, but structurally similar. A correction to the frame. Look at the universe from outside the KBC void, and you see a slightly different cosmos. Not a radically alien one. The galaxies are still there, the physics is still the same, the Big Bang still happened 14 billion years ago, but one where the expansion rate is lower than we locally measure, where the galaxy density in the local region is conspicuously sparse, where the Milky Way and its neighbours sit in a quiet underdensity that does not represent the average cosmic neighbourhood. An observer there, looking in our direction, would see the KBC void as a notable feature on the cosmic map. A large, clean underdensity in an otherwise structured universe, about as distinctive as the Boötes Void appears to us. And they would see us, inside it, measuring the universe from our biased vantage point, not yet having fully corrected for the asterisk. The next generation of sky surveys, including the Vera Rubin Observatory's legacy survey of space and time, the Euclid satellite, the Nancy Grace Roman Space Telescope, and the Square Kilometre Array, will map the distribution of galaxies and matter with unprecedented depth and precision. They will characterize the KBC void's boundaries with much greater accuracy than current estimates allow. They will measure the transition between the void interior and the surrounding walls. They will build the first genuine outside view of our local cosmic neighbourhood, from data precise enough to correct our local measurements for the bias of our position. The project is already underway, and when that correction is made, when we have a fully characterized map of the KBC void and a quantified estimate of its effect on our expansion measurements and our distance ladder calibrations, cosmology will be in a better position than it has ever been. Not because we will have solved every mystery, the universe has an inexhaustible supply of those, but because we will have removed one of the hidden assumptions that has been present in every measurement since the first redshift survey was taken. We will know where we are, not just approximately, not just in terms of the cosmic web's filaments and walls, but in terms of the statistical representativeness of our location. We will have corrected for being inside a hole. Until then, every map of the universe, every Hubble diagram, every plot of large-scale structure, every constraint on dark energy and dark matter, every model of cosmic history from the Big Bang to the heat death, carries that asterisk, a small notation that says, these measurements were made by observers living inside an anomalous underdensity, before the full correction for their position was known. The results are accurate to within the uncertainties of that correction. proceed with appropriate epistemic humility. We thought we were mapping the universe. We were mapping the inside of a void, and the universe, the full, corrected, asterisk-free universe, is out there, still waiting to be fully seen. Not from here exactly. Not from the centre of this enormous quiet emptiness we were born into, but from a perspective that accounts for where here is. A perspective that is still being built, one survey, one redshift, one corrected distance measurement at a time. The maps are being redrawn, the asterisk is being worked through, and what we find on the other side of that correction may be the most honest, most accurate, most fully contextualized picture of the universe that human intelligence has ever assembled. We are, in the grandest possible sense, still figuring out where we are, and that ongoing, humbling, exhilarating process of situating ourselves in a cosmos that is always larger and stranger than our current best picture of it, is what science is.